Hey everybody, and welcome to another video. Today we are going to take a look into something one of you was sending to me, a question namely from Nick, how we can compute the gravity assist maneuvers from Voyager 1 and Voyager 2. Now we are not going to make a deep dive from a theoretical perspective, but we are going to use Python to compute the heliocentric velocities of Voyager 1 and 2. And we will not fully cover the topic today, but I was thinking maybe this is a good starting point for another project idea where we can, for example, have some kind of interactive tooling to compute gravity assist maneuvers using Python and maybe some kind of UI. So let's see what we will build from here. But anyway, let's start with today's session, and I would suggest let's take a look first into what we want to achieve today. So Voyager 1 and Voyager 2 were starting back in end of 1977, and they're still operating, which is a very fascinating thing, I would say. But escaping the solar system is a rather challenging task. So what we see here, for example, from the Wikipedia page is the velocity trajectory, or the velocity, the heliocentric velocity of Voyager 2 versus the distance from the Sun. Now, what is the heliocentric velocity? It's basically the velocity, all components added together, with respect to the solar system barycenter. And the thing is that you need a certain velocity to really escape the solar system. And this solar system escape velocity is here, the blue line, and the function we will also provide later in Python. Now, in the very beginning, when we started our probe, we see that the heliocentric velocity was way too small to escape the solar system, which means that Voyager 2 at some point would have crashed back into the Sun. So the thing was to have some so-called flybys at the major planets like Jupiter, Saturn, Uranus, and Neptune to increase the velocity. The thing is, and this is interesting about the gravity assist, that as seen from Saturn or Jupiter, so in a Saturn or Jupiter-centric coordinate system, the velocity doesn't really change from the spacecraft. So it leaves the reference frame with the same velocity it entered. But if we switch back to this solar-centric coordinate system, we see some kind of velocity gain or velocity loss depending on the geometry. And again, this geometry is something we will figure out in a future video in a more interactive way. But today I would like to have a look at how we can obtain these data, these heliocentric data, so that you can play around a little bit with it and also consider also other spacecraft to compare it, for example, with, I don't know, Cassini, for example, or with New Horizons, and then also to compute the different escape velocities from the different planets, maybe to see how much energy has been gained. Now, the kinetic energy is something you may know. It's the mass times the squared velocity times a half. So you can even compute the gain of the energy in these sections here. You have to consider the potential energy and the kinetic energy, maybe also something for the future. This is just a small first compressed Cosmos video. But without any further ado, I would say let's go into the coding part to see how we can achieve this plot here and see that even after the Jupiter flyby we had enough energy to escape the solar system. For this, I would suggest to go to the Google Colab, or as always, you go to the GitHub repository, you click on the badge, and then it opens directly with all the code that we are going to code today. Of course, I already programmed everything, so it is more or less, it is a little bit already done, let's say. So it's not like free coding here. What we need today is SpicyPy. So Spice is like the library from NASA that can, that helps you to compute a lot of different trajectories and values and so on from solar system probes, or also from the planets and minor planets, comets, and so on. So it's a very powerful tool. And first of all, we need to install it. Now, the thing is that Spice works on something called kernels. So these kernels are like, I wouldn't say like databases, but they already contain a lot of pre-computed values for the spacecraft, and they are the most precise things you can get on the internet if you work, for example, with spacecraft data or in the space science community. The thing is that these values, you can download them for free on the NIF download server. I just create here 3 download commands, and this is like a wget command, which you can also execute in Colab. You just have to make the exclamation mark. Then here our -o, which indicates our file name, and then also here the link to the corresponding server, which is at JPL NASA. So it's being downloaded quite fast because the files, they are not that big. Yeah, as you see here, we can also generate code with AI now, with Gemini. Maybe we'll make a session in the future about this. I always say that it's super helpful if you are already familiar with coding, if you have some advanced skills, let's say. But as a beginner, I wouldn't suggest to start with the AI part, because it may give you some suggestions or some functions that are maybe you don't really understand, or you're not keen to understand because you would like to do some vibe coding. So I'm not the guy who says, oh, this is all bad and so on. It's more like a nice toolbox to have to boost one's productivity. But here we are to learn something, and I would say we do it hands-on, because otherwise we don't really need to learn anything if you translate everything with AI while learning another language. We need for our script also some libraries, like for example glob, which is good for finding files and so on. But also here, let's copy paste everything from my already existing cell. We have here pathlib and OS for all the file handling, SpicyPy, we have NumPy and matplotlib for the plotting later on. Because first of all, we need to find the kernel files, and they are per default downloaded in the files folder, and there we have these 3 files. Now to load them, they are in a folder called /content. We need to first download them, so to read them. So we have the kernel paths is equal to, and then what we can do is we can create some kind of list comprehension where we are then reading in the data. So we use pathlib path and then /content. So it goes through the entire content list directory and returns all returns then no, it is not returning anything. It provides the /content naming into our file. So we need to find the files also, and what we do, or how we do it, is with glob. And normally you would say, well, I want to list all the files, you know, with a dot. But the unfortunate thing here is that it would also list invisible files, you know, this files that only have a dot and then some naming. The hidden files, we do not want to do that. What we need to do is we need to get some kind of regular expressions. So we want to avoid anything that really starts only with a dot, so which has no name beforehand. So simply, if it's nothing dot any file, any name or ending, we want to get rid of it. We want to ignore it, because otherwise we are loading maybe these hidden files. And also we have to be careful, because if it's a directory, for example, it's also not that good. So we have to ensure that it is a file. By the way, you just saw some suggestion from Gemini, and yeah, it was not something I wanted to have. Maybe it should listen to the microphone, then it would know what I want. But anyway, so we have here now our 3 files, our 3 kernels. Now we can simply load them with spice.furnish. So furnish is like the simple function that helps us to load all the spice functions. We need to convert, though, the POSIX paths to a string, because otherwise we get an error from spice that cannot handle the pathlib paths. So let's go through the entire array and also then convert it as a string. So we now loaded everything. Spice knows now our 3 kernels. So the one kernel is from the Voyager 1, from Voyager 2, and a time kernel, which is also important. We have, there is some information about what's in the kernels Voyager 1 and Voyager 2. I would suggest I will leave a link into the description so you can read through the documentation. It's rather simple. It just lists all planets basically from 1970s to 2031, I think. So yeah, you can just compute all the positions in this time frame. Now, speaking of the time frames, I also have another code fragment I would like to copy paste here. It is the part where we are setting the timestamps. So the start of the Voyager 1 and Voyager 2 in UTC, it's September 5th and September. This is a mistake. It should be August. It's not September 5th, it is August. Now that's good that I was copy pasting it, so this is wrong. I think it should be the August 22nd, and I don't know the time, so we have to be careful here. Let me just quickly go back to the documentation. So you know what, I can show you the documentation. Just let me Voyager spice kernels. I have here my second screen. We can have a look at that in a moment. So these are the Voyager kernels. Perfect. So where's my browser? There we are. So we have here the NIF, the Voyager kernels, and then we go to the SPK, and then we have here the summary text file, and there we see the Voyager time frame, the Voyager frames, like we can compute Voyager with respect to Earth for a certain time frame and so on. Now this is the Voyager 1 probe, and here's the Voyager 2 probe, and it starts here August the 20th. So I would suggest we copy this one here, and then we have to switch back to our coding and put it here. Yeah, good. Anyway, and the end UTC, I set some artificial end UTC 2026, and also then we need to convert the UTC timeframes to ephemeris time. Now ephemeris time is like the standard time frame for SPICE. If this is your very first video, I would suggest to go back to the other videos so that you understand a little bit more what this SPICE thingy is all about. This channel already grew in a very organic and also unorganic way, so it's almost a little bit chaotic. Maybe I should make a very dedicated SPICE tutorial session, because otherwise it will be very difficult. So I hope you just follow me, and let's talk about a SPICE tutorial in the future. We have our starting times and also our end time, which is the same. So here just the January the 1st, and then we create a array from the first starting the launch time to the end time with 10,000 and 10,000 equal distant steps. Cool. So this is what we have now. And now what we're gonna do is we want to compute the heliocentric velocity and the heliocentric distance of our Voyager probes. So let's create simply the data frames, the lists there where we are storing these things. And what we are going to do is, you see it already fills up, it's crazy. We want to go through the ephemeris time, so the Voyager 1 ET array, there we are. And for each one we want to compute the position and the velocity. And position and velocity, they are stored in something called a state vector. So the state vector is 6-dimensional with x, y, z, and the vx, vy, and vz values. And we have to call spice.spkgeo, which is a function that just allows us to compute the state vector. And then we have to define the target. What is our target? In our case here, it's Voyager 1, whose code is -31. Also in the past, I showed where these lists are. Again, I am more convinced to have a dedicated SPICE tutorial series. It's really time. We have to determine or set the time, which is the ephemeris time, simply the float, which comes from the for loop. Then we have to set a reference frame. In our case, it's the Eclipse J2000 reference frame. This Eclipse J2000 is like the standard frame, which is like in a heliocentric coordinate system. And then we have to take an observer. So from which perspective do we want to compute the vector? It is from the solar system barycenter, which is 0. It's not the sun. The sun would be 10, because the mass of the entire solar system is not in the sun. It's in the solar system barycenter, that is, summarizes all, let's say, masses from all planets and also the sun. Now we compute the distance and the velocity of our Voyager probe. So how do we do that? We simply append it here, and we need to compute the norm of our last three values, the velocity we're talking. Yeah, the last three. So this is that. So from 3 colon. And our heliocentric distance is then the first three values. So let me just copy paste it here. So we see these are the first three values. Well, I also did this thing also now for our Voyager 2 probe, basically the same for loop, and then afterwards converting it into a NumPy array. So let's just copy paste it here. This is the second for loop, and these are the conversion parts. We can simply execute it, and we have no errors, which is nice. Cool. I would suggest what we can do now is we can create a plot as you have seen it before here. Yeah, the velocity versus the distance, and we can start with the time. So the velocity versus the time. And for this, we need to convert our ephemeris time array with the 10,000 entries back to UTC. And there's something really nice in SpicyPy. It is a function that allows us to convert it directly. So we make a list comprehension. We call spice.et to date time. Yeah, you see the auto completion. Let me just check. This looks legit, nice. But here we have to close the brackets. So there are no mistakes. Well, this is a nice auto completion. It is completely valid. Yeah, he wants to do it again. That doesn't really make sense. But yeah, let's stick with our conversion part here. So let me just execute this part. And then afterwards we can simply plot it. And yeah, well, plotting is a lot of, you know, making fancy plots and design. So there is no need to write everything line by line. So let me just copy paste everything. We can press the execution button. And what we get is the heliocentric velocity of Voyager 1 and 2. Here the velocity in kilometers per second versus the year. Well, this is a similar plot as we've seen here, just a little bit more cropped. This is like here to the way to the future. We see the velocity is not really decreasing anymore, so far away that it doesn't really, it's almost negligible. But what we want to do now is we want to compute it versus the distance. We computed the distance, but we also want to compute the escape velocity. And how do we do that? Well, first of all, we need to know the equation, and we have to, for this we need the gravitational constant, the mass of the sun, and for later for conversion we need also to know what is 1 AU, because we don't want to plot everything in meters or kilometers. It would be kind of insane. So these are like our gravitational constants. You can also extract them from SPICE with the right kernels, but to be very frank, I was lazy and I just copy pasted it from Wikipedia. Yeah, that's what people sometimes do, being lazy. But hey, as long as it works, it's fine for me. Not very scientific, but hey, we are not writing a paper, so I would say that's fine. Now what we do is we compute the velocity, and well, the first small thing what I did was a little bit hacky. I wanted to have the escape distances. Yeah, it's a little bit weird. I wanted to have the minimum and the maximum considering from Voyager 1 and Voyager 2, also in 10,000 steps. So it is like the minimum of the both distances and the maximum of both arrays. So we don't know, it's almost the same, but yeah, it was a little bit hacky and some fun. But what is now the escape velocity itself? And you see I'm looking right to my screen because I cannot remember anything anymore because technology helps me with that. No, jokes aside, the escape velocity is, oh my goodness, it's already auto-completing it. That's insane. It's not like the kernel, from Colab is linked with some other stuff. It's really completely fresh, so I really crashed everything and reconnected. It's really insane. Yeah, it is actually the square root of 2 times the gravitational constant times the mass of the sun, or any other mass, also from the Earth, if you want to compute the escape velocity for the Earth. divided by the current distance times not 1 AU. This is a mistake. Here it is times 1,000 because SPICE computes everything in kilometers and we need it in meters. So the AI was wrong here. Thank goodness. Yeah, but yeah, it's actually also a little bit absurd because afterwards, yeah, if we get our results, we have to divide it again by 1,000. It's not in the square root here. So these are now the values in kilometers per second. Yeah, that's what we need. Let's execute this part here. And then again, we can plot it as before. We also use our funny, nice plotting routine. And for those of you who are following my videos, you know that, yeah, my plotting style is, yeah, is somehow always the same a little bit. I have to really think more outside the box. This is really important in coding, not to go into always the same ways of plotting, for example. It's good to have a style, of course, your own style, but it's also nice to have something entirely new. Yeah, but anyway, let's plot it here. We have our heliocentric velocity versus the distance, and here as the green curve, we have our escape velocities, our escape velocity. And that's what we have here. We see that the green line is the solar system escape velocity versus the distance. We start at 1 AU, not at 0, like here in this plot, we start at 1 AU. And you see in the very beginning, well, no chance, but after the first flyby, which was according to Wikipedia at Jupiter, everything already looked nice, but you know, NASA wanted to gain more energy for the spacecraft. And if we look here at Voyager 2, and Voyager 2 is the orange one, it looks legit, I would say. Just the scaling is a little bit different. Our plot is way more stretched. Now the good thing is we have now our arrays with our heliocentric velocities. We can compare it with the escape velocities and so on. So this is a very first basic approach to compute the heliocentric velocities. And I hope you learned something using SPICE. I have some things already on my backlog. I think a dedicated SPICE tutorial would be nice. I did something in the past, but I think with more subscribers it would be nice to have a new part, considering also that I have some other science related news for next week. So stay tuned and thanks for listening.